Hello, hello. So, yes, today, again, kind of like last time, I'm going to diverge a little bit from only talking about UFO stuff because I happen to find this stuff really interesting, and I'll talk about early computers and stuff if I want to. So, if you don't like it, deal with it. Today, we're going to be talking about Wilhelm Schickard, polymath, inventor of the first calculated machine, and UFO witness. William Schickard, whose name sometimes will appear as Schickard, Schickart, Schickardi, like if it's in Latin, sometimes Wilhelmus Schickardi. But William Schickard was born to a Lutheran pastor's daughter and a carpenter in Herrenberg, Germany. He excelled mathematically and academically, earning degrees in theology and Oriental languages from the University of Tübingen, where he studied mathematics and astronomy under Michael Maslin. And pay attention to this picture. So this picture at the bottom is drawn by the Neckar River in Tübingen and is painted by Johannes Pfister in 1620. Johannes Pfister will come up later on because he was not only an illustrator and a printmaker, he was a mechanician that would be involved with helping construct some of these machines. He also illustrated that drawing to the right in kind of black and white of Tübingen. And after becoming a Lutheran minister, he collaborated with Johannes Kepler on engravings and calculations for Kepler's Harmony of the Worlds. And here we can see some of the engravings and illustrations he did for Kepler's Harmony of the Worlds. In fact, Kepler would actually kind of be good friends with Schickard. Kepler came back to Tübingen when his mother was accused of witchcraft, and Schickard was the Lutheran pastor at the time in Tübingen, and they kind of they became friends at that point when Kepler kind of came to town to help in his mother's defense against witchcraft, which was eventually later on dropped. In 1619, Schickard transitioned to academia as a professor of Hebrew at Tübingen, and he created innovative teaching methods and tools such as the Hebrew rota for Hebrew verb conjugation. What this basically was a similar kind of to almost like his calculating machine. It was a rotating cylinder that you could rotate in certain directions to conjugate various Hebrew verbs. And so he created mechanical devices even before this calculating machine to help teach people Hebrew. And he wrote books on this topic, on Hebrew, teaching Hebrew and other Oriental languages. But Schickard also had a deep interest in astronomy. And in 1623, he invented something called the astroscopium. The astroscopium is kind of, it's kind of like in between like a planisphere and like a two-dimensional star kind of like chart. It's a paper cone featuring the imagery of the starry sky. And these paper cones would be printed on paper, like in this book of his, and you would cut them out and fold them so they were taped together in a cone-like shape, like you can see here. And there was another kind of cone at the bottom, and with this, you could basically rotate it depending on time to see which view of like the night sky would be at any given time, you know. And you can actually make these yourself. There's this Kelly Magruder who has a PDF on making your own astroscopium, and I think that would be another kind of fun project that people could do, is to build one of these kind of paper cones of the night starry sky. And his work Ephemeris Lunaris, he developed a theory for the moon's orbit that allowed him to calculate the most precise ephemerides of the time, providing position values for moving astronomical objects. He was also the first to determine meteor trajectories using simultaneous observations from different locations. So he was really involved in geodesy and geodesic calculations and triangulations. I don't believe the triangulation theory was actually his own, but he apparently was the first to calculate these trajectories. And in fact, he was witness himself to a meteor event on November 7th, 1623, that he was able to take multiple observations and calculate its height and path, which he illustrates in this kind of woodcut here. Schickard was also a talented mechanic who designed many of his own instruments, leading Johannes Kepler to refer to him as the ambidextrous philosopher. In a letter in 1623, he created the very first calculating machine, which he termed the reckoner, or a calculating clock. This machine was capable of adding and subtracting numbers up to 6 digits. For more complex calculations like division, he used what was called Napier calculating rods, or Napier bones, which formed the cylinders that contained the multiplication tables. So these Napier bones were basically a way of doing calculation, lattice calculation using logarithmic tables. And so what they did is they took these bones, which were typically just kind of sticks like that with these tables, put it on like a sheet of paper, kind of like this, and rolled it around a cylinder so they could be rotated. And in fact, this kind of technique would later be used. This is a device from the later 18th century of Napier bones on rotating cylinders that, much like Schickard's calculating machine, you would rotate these cylinders around to determine what the right multiplication values were in these tables. Only, unlike Schickard's machine, there's no mechanical apparatus here to do the additional additions or subtractions or calculations. It would have been done on paper. But it was a similar kind of principle. And these are two drawings actually from Schickard's time of his machine. And you can tell they do look, kind of computing like, almost more like a cash register. But they do look like some sort of kind of mechanical calculating apparatus. This sketch on the right is one that's actually included in the letter to Johannes Kepler. The sketch on the left was actually found with some instructions to the mechanician that would be basically fabricating this machine on behalf of Schickard. And in 1718, so the first kind of references to this machine were published back in 1718 at the very least. One of the first biographers of Kepler published a collection of his letters that included 2 letters from Schickard to Kepler. And on one of these letters is a note by the publisher referencing Schickard's calculating machine. And in the index of this list of correspondence, they have it also listed as Machina Arithmetica on page 863. And so in this first letter, we can see that was sent to Schickard to Kepler on September 20th, 1623, detailing the results of his work in Latin. He says, "What you have achieved through calculation," Schickard stated, "I have just tried to do by way of mechanics. I have constructed a machine consisting of 11 complete and 6 incomplete, actually mutilated sprocket wheels, which can calculate. You would burst out laughing if you were present to see how it carries itself from one column of tens to the next column, or borrows from them during its subtraction." And you can see the publisher put a side notation here, the Schickardi machine Arithmetica. So there was, at least in 1718, a copy of these letters mentioning his publishing his calculating machine, or calculating clock, as it was called. In his next letter, dated February 25th, 1624, Schickard would deliver some unfortunate news to Kepler. And this was published in a further kind of complete Gesamtwerk, volume 18, that contained the basically correspondence from 1620 through 1630. And they published this second letter of his, which provides a little bit more detail of how the machine works and explains this unfortunate news that happened. That's the full letter. Then you can see this, that one illustration of the machine came from the second letter in 1624. And he also included a kind of a sketch of the gear mechanisms. He starts off with kind of the bad news here. And remember this guy I just briefly mentioned that did those illustrations, Johannes Pfister. "I have placed an order with the local man, Johann Pfister, for the construction of a machine for you. But when half finished, this machine, together with some other things of mine, especially several metal plates, fell victim to a fire which broke out unseen during the night. I take the loss very hard, now especially since there is no time now to produce a replacement soon." He then goes on to further describe the operations of this machine and how it works. "I will describe the computer more precisely some other time. Now I don't have enough time. A are the upper faces of vertical cylinders. So at the very top, it's hard to see, but those knobs at the very top of the machine say A, and that would be the rotation of those Napier calculation tables that are printed on the cylinders, whose side surfaces are inscribed with the multiplication tables. The digits of these tables can be hooked out of the windows B of a sliding plate. And so you would move these like wooden plates to be able to see what the numbers were of those various cylinders. From the inner side of the machine to the disc DD are attached wheels with 10 cogs, and each wheel is clutched with a similar wheel in a manner that provided some of the right wheel spins around 10 revolutions, the left wheel will make 1 revolution. But provide the first wheel spins around 100 revolutions, the third wheel to the left will make 1 revolution. In order for the revolutions of the wheels to be in the same direction, intermediate wheels are necessary. And again, that's a bit closer up image of kind of the gear kind of little sprocket sketch that he did here. And this again is that sketch of the that they found in Stuttgart, along with the instructions that were sent to Johannes Pfister on how to basically construct and manufacture the machine. Now, the machine was pretty essentially a basic, simple machine. In fact, the only mechanical aspect of it was this subtractor adder unit that used these cog wheels. The entire upper part of the machine with the rotating cylinders is really just for reference point, is so you know what to do with the adder wheels at the bottom here. And this machine was constructed using these various cogs and what's called a single tooth wheel there. And this was actually a problem, and it's kind of why this machine is limited to only 6 digits, is because the amount of force necessary to carry across all those wheels on a very large number would probably break that single sprocket. And so this was kind of done away with when Blaise Pascal would invent his calculating machine 20 or so years later. They didn't use single tooth wheels because they realized the problems of the forces that would be required to propagate a carry over all the gears with large numbers would be too much, and it could, break the mechanisms. But you can basically see how it would work. As each of these wheels would spin every 10 times, it would cause that really long sprocket to kick over and carry over in the next digit. And there's an excellent YouTube channel you might check out, JEPU Machines, the guy that built one of these, and he demonstrates the use and stuff. And these that kind of illustration of the gears up there is from one of his videos. And this is another thing with his videos where you can see the back of one of these machines. This is the back where they have these Napier bones on cylinders that just spin around. And you can see those bars that you pull out to the right or the left and the front to be able to see these various columns. And I'm going to try and do a simulation here just to kind of give you an idea of how this thing works here. Let me see here. All right. So this is a simulation, a simulator that was created in Scratch, and you can visit that link yourself and give it a try out. It's pretty easy to use, at least for basic operations. It uses an architecture known as abridged multiplication, which was kind of obscure for the time. It was some people aware of it. Kepler was aware of it, as well as a couple other contemporaries of Schickard's. But most people were just, quite frankly, not aware of how bridge multiplication worked at the time. And so that's the way this machine works. I'm just going to demonstrate a couple real quick operations. So addition is pretty easy. And remember, the mechanics of the machine is mostly the adder and subtractor mechanism. So let's just say I wanted to do basic addition of like 27. So put 7, I would turn this knob to 7, turn this knob in 2 places to 27, and I wanted to add 56 to it. So again, then I would just turn this knob again, 6, 1, 2, 3, 4, 5, 6, and this knob 5, 1, 2, 3, 4, 5, and that would be my addition, 83. And you can do the same for subtraction. In the real machine, you would just turn the knob the opposite direction. In this machine, in this simulator, you have to hold down the left arrow, which is kind of counterintuitive, and you can subtract numbers as well. But that's pretty easy to do. So what if we want to do some multiplication? Say I want to multiply the number 332 by 5. What I'd first do is I would turn these cylinders up here to the proper number. So 300, so 3 in the 300s place, 332, 332. So I've entered the number into up here, so these tables are in the right position. I want to multiply it by 5, so I click 5 over here to get the right numbers that I need to deal with here. Now, this is basically just telling me. Now, if you were looking at the Napier bones, these are typically done in a ratio of the 10th, like the carry place, and then the sub number. They just add them in the simulator here. So this tells me what I need to add in this column. So 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can see how that moved to 0, and it automatically carried the 1 over there. Now, you can save time, and since I knew that was 10, I could have just left this at 0 and carried the 1 over here. That's what I'm going to do for the next two. So then I'd move over to the next column. 15. 5, 1, 2, 3, 4, 5. The 1 carries 1. Then I move to the next column. 15 again. 1, 2, 3, 4, 5. 1 carries. 332 by 5 is 1,660. So this machine works by converting addition and multiplication operations to subtraction and addition operations that it then performs with your adder and register down there. Let's say I wanted to calculate 332 by 35 instead of 5. So first, I'm already halfway there. I've already got 5. And it's sitting here in my register. Next is 30. So the 3. So we're moving over one decimal place. I click 3. But because we're in the 30 place, these numbers get shifted over basically 1. So in this place here, I'm adding 6. 1, 2, 3, 4, 5, 6, 9. In this place here, I'm at 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And next place also 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 332 by 35 is 11,620. Now you can go all the way out. I've actually calculated 6 decimals by 6 decimals. So point, 1, 2, 3, 4, 5, 6 by 0.987564 or whatever. And you can do that again by just kind of keeping track of that decimal place. Since there's no decimal on here, you perform it as basically as if it wasn't a decimal, and you keep track of the decimal, and you kind of would add it back in later. Another kind of nifty feature that they had on this is that because you only had 6 digits you could work with in the register, if you tried to move this last digit over to 9 and then one more as if it would carry over, because there's no register, what this machine would do is it would beep, and we can see here, and that beep would remind the operator to put a ring on his finger, and that ring would add as kind of a reminder that he has 1 extra carry place that he needs to add back in when the calculation is done. And that's how they could work on numbers larger than 6 digits. Now, these buttons on the bottom are really, they're just helpful memory registers. Like, so when you're doing larger calculations, like by multiple digits, it can help to store like what you've already done down here in the bottom, so you remember, kind of what you've done. So it's a pretty simple machine. It's really just a basic adder machine that adds and subtracts, and uses an innovative method of a bridge multiplication with these Napier bones on cylinders to tell you what you need to add and subtract to perform these calculations. I think it's very cool. It's kind of fun to go play around and figure out how to use and figure out its operations. I would actually like to create my own Schickard machine eventually. I'd even like to make kits of these that kids could make that could be sold for like STEM kits to be sold in schools to teach people early computing, because we just did some calculations on a machine that is now 400 years old, over 400 years old. So I think that's very interesting, very cool. Now, in 1631, Schickard succeeded his mentor, Michael Maslin, as the astronomy professor at Tübingen. And he was a strong supporter of the heliocentric model, and he maintained collegial and friendly relations with Johannes Kepler. That year, he also invented what was the first handheld planetarium to illustrate the movements of the solar system. And you can actually see that in his portrait from 1631. You can see him holding it. And on the left here, we have what was a recreation. That's I don't remember what museum that's in, but there's a recreation of his handheld planetarium that we see him holding in his portrait here. Now, unfortunately, the 30 Years' War that ran from 1618 to 1648 had a profound impact on the later years of Schickard's life. After the Battle of Nördlingen, in September 1634, where the Catholic army, bolstered by Spanish troops, achieved a decisive victory over the Protestants, the victorious forces occupied the town of Tübingen. With them, they brought the bubonic plague, which severely affected the town's populations. Within the following year, Schickard would lose his wife, his children, his entire family to the bubonic plague, and would become the last surviving member of his family to also die of the plague, dying on or possibly just before October 24th, 1635. Now, with his death, now we know that Schickard tried to have one of his calculating machines created for Kepler, and that was destroyed in a fire. There essentially was a machine of his own that he had created. We do not know what happened to it. Unfortunately, it's probably likely it got destroyed or burned after he died from the plague. They likely would have burned his property and other things, and it probably just didn't survive. So we'll likely never see an original copy of one of these machines. And though his contributions were not really acknowledged in his lifetime, like I said, Blaise Pascal, who many people think of, and for the longest time thought invented the calculating kind of machine, wouldn't invent it for 20 years. But to be fair to Pascal, he would not have been aware of Schickard's machine. In fact, it's doubtful most people were aware of Schickard's machine until it was kind of rediscovered, in the last century. So his contributions may have not been acknowledged at the time, but they are acknowledged now, and he is commemorated with the Wilhelm Schickard Institute for Informatik at the University of Tübingen, which is basically the German way of saying the computer science department. And the Wilhelm Schickard Schule in Tübingen is also named after him. Now, after years of experience in these astronomical observations and calculations, William Schickard witnessed a remarkable celestial event on January 25th, 1630. This event could be likened to a classic UFO sighting today. However, as the hours passed, the observation grew increasingly strange, evolving into what has been referred to as a miracle sign or miraculous sign or air battle, raising skepticism among some of his academic peers at the time. Despite this, Schickard, as a direct observer of the event, was committed to documenting this phenomenon as accurately and as scientifically as possible. In his 33-page manuscript, I'm not going to read the German here, but it basically says, description of the miracle sign seen in the evening of 7 o'clock on the evening to the 10th in the morning in the clear sky towards the north. And this was printed just 2 days later on January 27th, 1630. And as he kind of details the event. I think that's pretty remarkable. It was printed 2 days later. To be honest, I'm not sure how he wrote it and they typeset it. Maybe they just mean he turned it in for print 2 days later, and so that's the date they put on it, or he wrote it 2 days later. I don't see how they could have had this actually printed within 2 days. But that's kind of besides the point. Schickard details the event in this document. And I'm going to kind of stick to mostly his words because I think for this and the other case, because I think it's important to hear it as they say it. Take into consideration here, when translating 400-year-old German manuscripts, it can be kind of difficulty, and the translations can be kind of a little iffy because they don't use some of the same words that modern German uses. Their sentence structure can be odd and kind of weird. The way just the books are printed and formatted without any real sentence structure is kind of weird. So uh, I've translated these as best I could with some help from some German speakers, but there might still be a little kind of iffy or weird sounding translation here. And this is the problem when dealing with a lot of these old cases, is that there's could be stuff we're just missing in translation that we just are not understanding correctly. But so this is what he says. As I, in accordance with my habit, contemplated the stars in the then clear sky, and after a long southern observation, finally turned my gaze to the northern sky, an unexpected phenomenon presented itself, a snow-white material, which I cannot well call a cloud because it was not so fleecy or fringed at the edges as natural clouds usually are. Instead, it was quite smooth and polished, perhaps somewhat brightened by reflection. It also cannot easily be called vapor, because it had a specific, constant, and elegant oval shape, whereas vapors otherwise flutter around in an unstable form. Not to mention, it far surpassed the ordinary clouds in brightness and radiance, being completely pure and homogeneous in nature. After he makes a few more astronomical observations, he returns to the description of the object. In this first apparition, I am astonished by the unusual brightness and arouses in me the suspicion of a vende, which I looked up, basically Latin at the time, is to see a meteor. The resident concern of the new papers. Now, this is one of the things that had problems with translation because it says like Neuen Zeitungen, which I guess refers to when they say new papers, printed papers as opposed to handwritten papers. So the newly kind of printed papers. Whoever doesn't understand anything about the sky, to him it may well appear at first as a common cloud. But I looked at how the sun was hovering in Aquarius at that time, around 7. But I looked at how low the sun was already below the horizon, and how much lower the moon after its last quarter was still below Scorpio, that it was thus naturally white, that the two celestial lights were then quite impossible for a cloud in the same position to light up just a little, to become so bright that it would give off such a clear glow. And even if some peripatetic of Aristotle wanted to say whether perhaps the vapor has risen higher above the usual barriers of the air, that the sun's rays might have drawn it up next to the earth, then the day that passed, again, the season's custom was warm and finally bright, as is the best spring. Yet soon afterwards, at the oval figure before, in the right side toward the right hand towards the Lyra, a black dark color has shown, which sides indeed without doubt turned closer towards the sun and moon, and therefore must shine much brighter than the others when they receive the light from there. So it follows once again that this appearance was not natural at all, but the true root and origin of the miracle. And that's sounds a little weird. Like I said, there's not like full sentence structures. They break things up into these like brackets, and it's just kind of comes off kind of weird, but you kind of get the general idea there. And being a man of science, Schickard was not quick to write this off just as a miracle. He hoped to kind of find some sort of scientific explanation for what he was witnessing, and he states, however, I must, in order to more thoroughly dispel all doubts, honestly confess my own initial suspicion, because in this case I am neither gullible nor willing to allow miracles, since all human wisdom would then be lost to the matter, could no longer be explained by natural reason. I looked in all the heavens to see if I could find any remedy, but found nothing other than the bright star Venus, which stood about 60 degrees, according to the eye, to the left, and shone very beautifully. As the often bright part was inclined almost exactly towards the same planetary star, while the dark part was actually facing away from it, I considered the former to be light transmitted to it, and the latter to be its shadow, as the ancient astronomer Tycho Brahe also testified that the comet Schweif in the year 1577 was not directed towards the sun like others, but towards Venus. And I also remembered from my own limited experience that Venus can illuminate a dark body from afar, as I often did, and most recently on Epiphany Day, the 6th, in the evening, when the young crescent moon was still more than 10 degrees from it, and yet evidently illuminated by it on its dark side. He then goes to report on the phenomenon after 7 o'clock, and this is where it gets kind of really interesting, and the multiple objects come into play here. This bright shining mass did not remain alone for long, but soon acquired two skins, one from the left, somewhat lower than the rhombus star of the dolphin, which looks not unlike a dolphin, and it had the shape of an overturned cauldron, or in summer, a haystack on the meadow. The other, on the right, however, towards the foot of Alleghetti or Hercules, which this image stretches out from the ground as if to trample the head of its trachea, this one has the shape of a long waystone, which has been ground down in both places. The kind reader will forgive me for using such silly similes. I cannot figure it any other way unless I have time to paint it with lines. These two, or rather all three colors, were snow white, but not just a bad white, like chalk or milk, which give no shine, but rather brilliant and shimmering, so that the area here was illuminated. The light was not luminous, like the reflection of a lying mirror or still water, but rather it swayed and agitated, and it did not sway as quickly as the fixed stars, but rather gently and roughly, like the waves of flowing water. Afterwards it grew, rose slightly, and then disappeared unexpectedly, but soon came back and repeated this change several times, so that one did not know whether it had really disappeared or it was only hidden. And this is how it had appeared up to that point towards the northwest. So, in summary, Schickard describes a bright oval or egg-shaped object in the northern sky, distinctly different than known clouds due to its smooth and polished appearance. After further observations, he noticed the emergence of two additional white objects besides its oval shape, each displaying different shades of colors of white. One resembled an overturned kettle or a haystack in a summer meadow, and this is one of the weird words, Überschock, that they kind of used, that shock refers to like a haystack. We can never figure out what the first part of the word was supposed to mean, maybe like lard, Oberschock, whatever it was. But so essentially like a haystack, and you can see this does kind of look like a haystack on a meadow down there might look like. And the other object looked like a long sharpening stone or waystone with both sides already worn down and so he used familiar objects of his time for the reference. And I like that Rachel made those little illustrations for me. So thank you, Rachel. So these objects shimmered in a way different from the hurried twinkling of fixed stars, prompting Schickard to wonder if they had truly vanished or merely hidden from view. So while this summary captures only a fraction of Schickard's observations, his manuscript spans 33 densely printed pages. The quality of his account is enhanced by his extensive background in astronomy and natural observations, highlighting his reputation as one of the foremost polymaths of his time. Like I said, he was the first guy to calculate triangulation to calculate the paths of meteors as they came in. He created some of the most accurate survey maps and kind of sort of revolutionized like precision surveying kind of at the time. Using his various geodesic calculations of the time. But ultimately, watchers must decide whether to accept Schickard's distinctions from known natural phenomenon like clouds and his interpretations of an otherworldly miraculous sign. In the context of modern UFO sightings, notable parallels emerge, particularly with frequent reports of egg-shaped or oval-shaped UFOs in contemporary literature. Like we had seen in my previous presentation on the Wilhelm Valençol case here on the right, which has a lot of similarities with the Socorro case. Oval or egg-shaped UFOs have been part of the literature for many years. Now, Schickard, who had previously suffered controversy in his life over his heterodox religious beliefs, would receive pushback over publishing this publication on his miracle signs. In a contribution to the collection of writings of the Tübingen Schickard Symposium on the 400th anniversary of his birthday, religious scholar Ulrich Bubenheimer, in his paper Wilhelm Schickard in the context of the religious subculture, explains the debates with a Tübingen theology professor, Lucas Osiander the Younger. In 1630, Osiander threatened to censor a work of Schickard that was in print, in which the latter had described two celestial phenomena and interpreted them as miraculous signs. Schickard saved the print with temporary feigned humility towards Osiander, as he wrote to his brother. Osiander was offended by Schickard's attempt to interpret the celestial phenomena prognostically. Osiander had already spoken out against the many prophecies and chiliastic apocalyptic interpretations of the time in a 1621 work. Furthermore, Schickard's view which was also current in the Tübingen circles at the time, that God sometimes speaks to his followers in dreams, must have smelled a spiritualism to the Tübingen orthodoxy, especially since Schickard took up the idea in this context that prophetic interpretations require higher inspiration, often only given to simple idiots. Osiander may have also suspected Schickard of adhering to esoteric future predictions in the manner of the Kabbalah Arithmetica, which he, Osiander, had polemicized in 1621. This suspicion could have been fueled by Schickard's repeatedly expressed interest in Kabbalistic numerical speculation. In 1621, Osiander placed the Kabbalah Arithmetica alongside the Rosicrucian Utopia. This accusation that Schickard was associated with Rosicrucian circles in Tübingen had already been made against him a few years earlier. Now, part of the reasons why people had kind of tied him to Rosicrucian circles is, in fact, because he was tied to Rosicrucian circles. Schickard's close contacts with this guy Christopher Besoldis were cited as his heterodox tendencies at the time. Christopher Besoldis was a juror, a lawyer at the time in Tübingen, who was also close friends with Johannes Kepler. In fact, he was a juror on Kepler's mother's case of witchcraft that had later been dropped. Besoldis is also perhaps more famous, I would guess, would be for his involvement with the Rosicrucian Manifesto. In fact, the Rosicrucian philosophies and manifestos were considered to be based on Christopher Besoldis's work, Tobias Hess, and this guy Johannes Valentinus Andrea. In fact, they together with mostly Andreas are considered to be the authors of the chemical writing of Christian Rosenkreuz. So, in fact, Schickard was hanging out with all the creators of the Rosicrucian kind of philosophies, and is considered one of this guy Christopher Besoldis back here is considered one of the kind of founding peoples of Rosicrucian philosophy and beliefs. He's also kind of well known for what he considers the justification of the natural law. To him, natural law was that human beings, we have free consciousness and we have the natural right to believe whatever we want to believe. Nobody can force us to believe anything. And the most natural law of all humans is that we have the innate ability to choose what we want to believe. So that's kind of another thing that this Christopher Besoldis guy was used to. So you can see with his connections at the time that he would have been kind of on the outs with the Orthodox religious people. In fact, like Tobias Hess with this other guy, Simon Stedion, kind of wanted to abolish the papacy in 1609. And so these guys were kind of had a lot of controversial beliefs, and Schickard and the rest of them were kind of all close buddies hanging out together. Now, this is not the first air battle or miraculous sign to actually be seen in Tübingen. Earlier in December 5th, 1577, near Tübingen, Germany, a remarkable phenomenon resembling large, high, broad hats emerged from the clouds surrounding the rising sun, blanketing the ground below. This event is dramatically illustrated in this broadsheet that was published the following year in 1578. And we can see this, I think it's a beautiful illustration here of these raining hats kind of falling on the ground. And this is the rest of the broadsheet now the broadsheet, surprisingly, is really mostly just like a religious polemic, like that doesn't actually talk about the sighting all that much, like only briefly. It's mostly full of other superfluous stuff. So while the image of an army marching through the clouds is a common element in many celestial visions of this period, the more intriguing elements of this image are the ghostly double sun that seems to peek through the clouds and shower of hats following to the earth. Pierre Basteau, in his History of Prodigies, so History of Prodigies, second edition in 1594, also describes this event in a bit more detail here. And this is an illustration that was also that was included in this History of Prodigies. Now, this second edition, Pierre, and again, I apologize for butchering pronunciation names here, Pierre Basteau, was already dead at this point. They actually took his first edition of the book, and several other people added stuff onto it. But it was printed in this 1594 edition of this book here. And I'm just going to, again, bear with the translations. The translations I mostly got on this one from another document I'll mention here in a second. But I think it's best to just kind of read what they have to say about the case. In the city of Althoff and its surroundings, in the land of Württemberg in Germany, 1 league from the town of Tübingen, it was seen on December 5th, in the year 1577, at around 7 a.m., that the rising sun appeared not in its natural clarity and splendor, but instead wholly yellowish, as at times does with the full moon, and resembled a large round barrel, shining so little that it did not dazzle, but could be contemplated freely. Shortly afterwards, its surroundings grew quite dark, as if eclipsed, and the sun was red as blood, so that we could not tell if it truly was the sun. Just then we saw two suns, one red, one yellow, which clashed together, and one seemed to replace the other, as can be seen during an eclipse. This lasted some time, until the other sun vanished, at which point we could only see the first dim yellow one. Shortly afterwards, there appeared a small black cloud shaped like a ball or a large plate, which dashed straight towards the sun and covered its center so that we could no longer see more than a great yellow circle. While the center of the sun was thus covered, another small, long, blackish cloud appeared. It fought with the sun, and they covered with each other several times until the sun eventually recovered its aforementioned yellowish color. Now, at this time, a black cloud appeared from the west towards the sun, and from it emerged a large number of people dressed in black, armed like soldiers, both on foot and horseback, marching in formation. This procession prepared to move across the sun and drift away from the east, accompanied by additional clouds, some red and others yellow like saffron, that seemed to rise from the sun's gloom and encircle it. And in this illustration, we can see all these soldiers on horseback and walking dressed in black. Next, out of these clouds came reverberations resembling tall, wide hats. And all of the ground appeared to be yellow and bloody and seemed to be covered by tall and wide hats. Those hats were of diverse colors, red, blue, green, and most of them black. Afterwards, these clouds descended like fog, and it seemed to rain blood, not only in the sky, but all over the ground and on the men's clothes, and everything we saw seemed bloody and yellowish. So what were the residents of Tübingen in 1577 witnessing the skies above town? Researchers Martin Schau and Chris Auerbach addressed this case in their Invasions of the Solar Bubbles catalog. And I'd like to thank Chris Auerbach for sending me a copy of this catalog this week so I could check this. And most of the work on this 1577 case and the sources I got basically turned on to from looking at his work. And I kind of tend to agree with their analysis here because it kind of fits in with many of these other kind of earlier cases and broadsheets, such as the Nuremberg event. The depiction of the army marching in the clouds may well be a satirical commentary on the contemporary conflicts of the time, possibly referencing the battles of Wenden or concerns over the Treaty of Bergerac. The blood-red light illuminating the observers and the shower of the hats following the procession could symbolize the casualties of war. Bostow's account concludes with the moral urging people to amend their life, suggesting a deeper significance to this event. Notably, the date in question, the sun was still below the horizon at 7 a.m. local time in Tübingen when this event was supposed to take place, which raises some questions as to the authenticity of the account. However, minor discrepancy in timing may not be significant. As you know, it's hard to get accurate times and witnesses on a sighting that happened 2 days ago, let alone one that happened 400 something years ago. Whether they saw it actually an hour earlier or not, or somewhere in the time calculations were not taking something into consideration, it's possible that there could just be minor discrepancy in the timing. But if it was in fact at that time, the sun was still below the horizon and would not have actually been visible, which could indicate that this was basically just kind of like a metaphor that was being published and was not an actual event. Celestial phenomenon in the 16th century were often interpreted as omens, and the motif of an army in the clouds was common for the era's visions. And if you recall the famous Nuremberg broadsheet event, which many people put up as a very early UFO sighting, in my opinion and many others, in fact, it's not even an event that actually happened. It's not real. it was just something printed in a paper to basically tell a metaphor to express some of the contemporary concerns and worries of the time. That it was not actually real, and this could be, in fact, be what's happening on this broadsheet as well, is that it was not an actual real event. It was really just meant for religious purposes, essentially. But if it was a real event, what could have they been seeing? So the hats mentioned could reference size, as seen in historical uh, UFO cases. Um, Bostow's vivid description might evoke images of flying saucers with their kind of raised crowns and wide brims. The nature of these hat-like phenomenon raises questions as to whether they were actually physical objects, or did the description stem from a misinterpretation kind of during the translation of the text. It's possible that they refer to lenticular clouds, which can be shaped like hats, like we can see in some of these illustrations, and they can create unusual sights under certain conditions. The colors described might indicate iridescence of, or like a mantis cloud formation, often associated with thunderstorms. And the term reverberations, which again is a term that perhaps doesn't make much sense. Perhaps it's a bad translation, but it could also suggest sounds reminiscent of thunder, which are also frequently noted in various contexts where you see clouds in situations like this. So, and Jack Valet briefly mentions this case with Chris Auerbach in the book Wonders in the Sky, which again lists the sources that I used here. So with both of these cases, again, we are left with essentially 400-year-old written manuscripts that uh, we just have to trust that the person saw what they said they saw and were reliable witnesses. There really isn't a whole lot more you can do with it. It's up to, I guess, the watcher to decide whether or not they trust the observations by these people, or whether there was prosaic explanations. I think in the case of Schickard, he did actually see something. Whether you can trust his observations, that they weren't just clouds, that's up to you to decide. I think in this later case, I think it's likely there was not even a real event. And if you look at that original broadsheet, it is mostly religious. Like it seems to mostly be just using that event for other purposes, which was common at the time. And I think that's what's also happened with like the Nuremberg broadsheet and potentially even other broadsheets from the time period. And that's that.